Gotta Keep Them Separated is an episode of the Degrees of Freedom Project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. In this video, Gotta Keep Them Separated, is the first in a series of videos that address the most common unit operations in material balances. In this one, we discuss the mixer, the divider, and the separator. For these three, mass balances and mole balances use the same equations because both mass and moles are conserved. The next three videos, when you saw what was the extent of your reaction, parts 1, 2, and 3, address chemical reactors as modeled with the extent of reaction and fractional conversion. Moles are not conserved in chemical reactions. A process flow diagram, or PFD, consists of a series of processing units, also known as unit operations, connected by flow streams. There are a great many unit operations. 4 that find frequent use in a process are the mixer, the divider, the separator, and the reactor. But we're saving the reactor for the next 3 videos. The equations we're going to develop are for open steady-state systems. Large chemical processing plants always try to operate at steady state. For expensive or boutique chemicals like pharmaceuticals or biological reagents, you'll see batch systems. But again, for the large chemical processing plants, you almost always have steady-state systems. For a mixer, it's usually represented as a set of 2 or more incoming streams and 1 outgoing stream. The general balance equation for a mixer reduces to the sum of the input flow rates equals the output flow rate. For each component, or chemical species I, the molar rate of species I exiting the mixer is equal to the sum of the molar flow rates of species I entering from stream 1, 2, and so forth, up to stream K. Overall, a total balance yields that the total number of moles exiting is equal to the sum of the molar flow rates of each entering stream. In a stream, the total molar flow rate is the sum of the molar flow rates of all the individual species. As a reminder, there is no chemical reaction in a mixer. A mixer is used to combine or mix together the input species. Physical mixers can be as simple as a pipe T-junction or as complicated as a stirred tank. Again, since mass is also conserved, the mass equation for a mixer are the same as the mole equations, with the n's or n dots replaced by m's or m dots. For a divider, the diagram shows that we have 1 entering or input stream and 2 or more output streams. The general balance equation for this open steady-state system is that the molar flow in the input is equal to the sum of all the molar flow rates in the outputs. For each component, or chemical species I, the molar flow rate of species I entering the divider is equal to the sum of the molar flow rates of species I exiting from stream 1, stream 2, and so forth. Overall, a total balance yields that the total number of moles entering is equal to the sum of the molar flow rates of each exiting stream. Again, in a stream, the total molar flow rate is the sum of the molar flow rates of all the individual species. There is no chemical reaction in a divider. Also, unlike the mixer, the mole fraction of species I in a stream is equal to that in any other stream. In other words, a divider simply divides the input stream. It doesn't separate out the individual components. The mole fractions are defined as the moles of species I over the total number of moles, or in terms of flow rates, the molar flow rate of species I divided by the total molar flow rate in that stream. A divider is used when a single stream needs to be divided up into 2 or more streams. For example, an individual chemical reactor may be too small to process all of your desired feed. In such a case, you would need to divide up the input into smaller streams and feed each stream into its own reactor. Such a scheme is known as parallel processing. Also, a purge stream may need to be in a recycle loop, and a divider would need to be used to divide out the purge stream from the main stream. A divider may be as simple as a piping T or as complex as 1 or more T's with a set of metering valves. Again, since mass is also conserved, the mass equations for a divider are the same as the mole equations, with the n's or n dots replaced by m's or m dots. Separators are the things that occupy most of the physical space in a chemical processing facility. Common separators are distillation columns, absorption columns, liquid-liquid extractors, gas strippers, filters, cyclonic separators, and osmotic membranes. A separator may have more than 1 input and more than 2 outputs, but we try and stick with separators that have a single input and 2 outputs. For the open steady-state separator, the sum of the molar flow rates of all the input streams has to equal the sum of the molar flow rates of the output streams, again with no reaction. You often specify the split fraction for a given species. The split fraction of species I with respect to stream S is the molar flow rate of species I in stream S divided by the molar flow rate of species I entering the separator. In other words, it's the fraction of species I that exits in stream S. T sub I1 is the split fraction of species I with respect to stream 1. If we only have two exit streams, then the molar flow rate of species I in stream 1 is the input molar flow rate times the split fraction, and the split fraction with respect to stream 2 has to equal 1 minus the split fraction with respect to stream 1. If the split fraction is the same for all species, then the separator is just a divider. The split fractions must be different to affect a separation. The values of split fractions are governed by phase equilibria, which is the subject of future videos. For now, we will assume that the split fractions are given parameters. The takeaways from this video are 1. In a mixer, the molar or mass flow in the output stream is the sum of the molar or mass input flows. 2. In a divider, the molar or mass flow in the input stream is the sum of the molar or mass output flows. Also, the composition of each stream is the same. And 3. In a separator, the molar or mass flow of a given species in an output stream is the split fraction for that species and stream times the molar or mass flow of that species in the input stream. Thanks for watching. This video is brought to you by the DOFPro team.